So let's look at part 2 of the question. Part 2 of the question, you're told that as the scientists now model the thickness of ice on a pond. In winter, the surface of water in the pond freezes. Once the thickness reaches, so let's say this is a pond. We are going to just, this is ice, right? This is ice here. Layer of ice. And this is the water pond in the water. So once, if it's the layer here is 3 cm, it's safe to skate. So 3 cm is safe to skate. The freezing of the water is modeled by a differential equation in which the rate of change of thickness of ice is inversely proportional to its thickness. Okay, maybe I type this out. The keyword here is rate of change of the thickness. Rate of change. Change of the thickness of ice is inversely, these are the keywords, inversely proportional to its thickness. Okay, great. Okay, great. So this part here is important because we need to let the thickness. So let thickness at time, maybe let thickness at time t be x cm. Okay, so I'm just gonna let it be x cm. At time t, that's the thickness. So to understand this phrase here, the rate of change of thickness, meaning to say this is dx dt, is inversely proportional to its thickness, meaning to say this is 1 over x. Okay, and it's an increasing function because in the winter, the what do you call it? The thickness of ice is increasing, right? So that is important. So once that's done, it's given that when t is 0, or t, did they give us t as a thickness of water? It's given that when t is at thickness is t. Thickness of the freezing water by the inversely proportional to thickness t. Okay, great. Well, let me check. Great. So they already labeled for us the thickness is actually capital T. So I'm just gonna let this be t instead of I let it be dt is actually proportional to 1 over dt. Okay, so that's pretty okay. Now once that's done, we are going to find you're told that at t equals to 0, at time t equals to 0, thickness would be 0. The thickness is 0 cm. T is in, small t is in minutes, after 60 minutes. Okay, so the small t is 60 minutes. Thickness becomes 1 cm. Now this is boundary condition, so this is also important. So once this is inversely proportional, just write this as dt equals to k 1 over t 1 over big T. So where k is a positive constant. Okay, that's okay. So once this is done, this is a pretty okay question. This is t dt dt t. So this is integration of dt, capital T, k, small t, and this will give us t squared over 2 equals to k t plus c. So just bring down the so when t equals to 0, when small t equals to 0, capital T is actually 0. So this render c to be 0. Is everything is just 0. So when t is 60 minutes, and t is actually in is 1 cm, right? So we could actually find our k here. So 1 over 2 equals to k times 60 plus 0. So k will just be 1 over 120. Okay, so find the time. Okay, great. So this case here, what we get is actually just t squared over 2 equals to k, which is 1 over 20. Remember, t is in minutes, okay? Because time t is in minutes. because they gave you in minutes, right? So that's in minutes. So find the time when the freezing commences until when the freezing commences means from t equals to 0 until the ice is first safe to skate on. So safe to skate at t equals to 3 cm. Okay, so when t equals to 3 cm, with 3 square over 2 equals to 1 over 20 t. So this will be t 9 over 2 times 120, which is actually 540 minutes. Okay, there you go. This is how you do this part here, meaning to say you need 540 minutes from the time it starts freezing, means t0. Okay, so this is how you do this question here proficiently. Any question or comments, please do let us know. Keep practicing and I'll see you in the next question.